Welcome to our video lecture on the pH scale. Our essential idea for today, the pH scale is an artificial scale used to distinguish between acids, neutral solutions, and basic or alkaline solutions. Our objectives for today, we're going to define the pH scale. We're going to review logarithms because who doesn't love a little math in the middle of their chemistry? We're going to find pH and pOH when we're given the concentrations. Then we're going to go backwards and we'll find the concentrations if we start with a pH. So here's a lovely graphic of the pH scale. Remember from middle school and your first year of chemistry that water has a pH of 7. Things that have pHs greater than 7 are basic. Things that have pHs less than 7 are acidic. And generally, the further away from 7, the stronger the solution. So we're going to have most acidic things here down in the 1s and 0s. We're going to have things that are most basic here in the 13s and 14s. Most of the time we talk about pH going from 0 to 14, but we can have negative pHs. We can have pHs greater than 14, but not really in nature. Most of the time, natural substances stay here in the middle of the pH scale just because things that are very extreme are highly reactive and they wouldn't keep that super strong pH. So pH is based on the idea of logarithms. So here real quick, we're just going to review what even is a logarithm. Remember that logarithms are all about finding exponents. So if I'm taking log base A of some number, I'm looking for the exponent. So basically A to what power is equal to that number that we're given. A to what power gives us n. That base of A to what power gives us that number n. The exponent, that power, is what we are looking for. So looking at this example, log base 2 of 8, I'm trying to figure out 2 to what power is equal to 8. You know that 2 to the third power is equal to 8, and so log base 2 of 8 is equal to 3, because 3 is that exponent on the 2 that gives us 8. Log base 5 of 25. 5 to what power is equal to 25? We know that's equal to 2. If you don't have a number, if you don't have a base, that's what we call the common log, and it's going to be a base 10. So there's an invisible 10 in there. So log base 10 of 1,000, we know that 10 to the third power is 1,000, so the common log, or log base 10 of 1,000, is going to be 3, because 10 cubed is equal to 1,000. How about if I have 1,000th? So this is the same thing as 1 over 1,000, or 1 over 10 to the 3. Remember that if you have exponents in the denominator, that's the same thing as a negative exponent. So 0.001 is going to be a negative 3 power on a 10. So the common log, or log base 10 of 1,000th, is a negative 3. This one, I cannot do this one in my head. I'm sure there are some people who can. I'm not one of those people. But we can pull out our handy-dandy calculators and plug in log of 0.0375. And it looks like it's equal to negative 1.42596, so many digits. So interestingly, when we do sig figs with logarithms, we're going to keep the number of decimal places in the logarithm equal to the sig figs in my number. So I've got 1, 2, 3 sig figs here, so I'm going to keep 1, 2, 3 decimal places in my pH. That 9 is going to turn that guy into a 6, so negative 1.426 will be my answer with a sig fig check. So pH is based on this idea of logarithms, and this formula is given to us in our data booklets. If you look at topic 8.3, in those first couple pages that give us lots of constants, conversions, and formulae, we are given that pH is equal to the negative log base 10 of the common log of the hydronium ion. That's pretty much the same thing as a hydrogen ion. Remember that when water dissociates, one of those hydrogens from one water molecule is going to jump onto another water molecule, making this guy hydronium. And this happens because there's an H+. So H pluses from water or from any acid, these H pluses are going to jump onto those non-bonding pairs of electrons on the oxygen side of a water molecule and make hydronium. So the concentration of the hydrogen ion is going to be equal to the concentration of the hydronium ion. We're going to take that concentration, we're going to find the common log, or log base 10 of that number, and that's our pH after we make it negative. So the negative log base 10 of the hydronium ion or the hydrogen ion, this is pH. So if my hydrogen ion concentration, remember that this means concentration, that hydrogen ion concentration is equal to 0.502 moles per cubic decimeter, then I can just take the log of 0.502, and the log is negative 0.29929, lots of digits. But since I'm looking for the negative log, the negative version is going to be positive. So the pH is going to be 0.299. That's our pH. How about this guy? 0.000024 moles per cubic decimeter. If this is my hydrogen ion or hydronium ion concentration, the log of 0.000024 is equal to negative 5.61978, lots of digits. But since I'm looking for the negative log, I'm going to do negative 5.6. That makes it a positive 5.619. I have 2 sig figs. I'm going to keep 2 decimal places in my logarithm. That 9's going to turn that 1 into a 2, and I have a pH of 5.62. So the reason that, if you remember back in our essential idea, I talked about the pH being, the pH scale being an artificial scale. There's no actual measurement for pH, right? We're measuring the molarity, but then we are arbitrarily turning this into a logarithm. And the reason is that's just too many zeros, and this is even more too many zeros. So it's far more convenient to express this as this than it is to make sure that we're counting all those zeros every single time. Way easier to write a 5.62 than 0.000024. Good? All right, let's keep going. If I have a concentration of 1 moles per cubic decimeter, then I can actually do this one in my head. I don't need to check my calculator. So I know that 10 to the 0 power is going to be equal to 1. Negative 0 is the same thing as 0, so my pH is actually 0. And you can plug it into your calculator if you want to. The common log of 1 is equal to 0. This guy also, because I have just a 1 here, I can figure out what the pH is without my calculator. So let's do a quick decimal move to turn this into scientific notation. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this guy is 1 times 10 to the minus 13 power. 10 to the minus 13. The exponent on the 10 is negative 13. I'm going to turn that positive. The pH of this solution is 13. Again, so much easier to write 13 than all of those zeros. Let's do one more. We'll do this one also without our calculator. We're going to go 1, 2, 3, 4, 5, 6, 7. This is 1 times 10 to the minus 7. That means that pH is going to be the negative log of 10 to the minus 7. That negative 7 gives us a pH of 7. This is a neutral solution, not an acid. So let's go ahead and look at doing this with actual acids instead of just concentrations. So if I have 3 molar hydrochloric acid, I know that hydrochloric acid is a strong acid. It completely dissociates. That means that every one of my HCl's, I'm going to get 1 H plus and 1 Cl minus. So if I have 3 moles per cubic decimeter, 3 molar hydrochloric acid, I'm also going to have 3 molar hydrogen ion concentration. So to find the pH, I'm going to take the negative log of that hydrogen ion concentration, which is 3. Negative log of 3 gives me a pH of, oh my gosh, it's negative 0.47712, lots of digits. We're going to keep 1, 2, 1, 2. That 7 turns that into an 8. So our pH is about a negative 0.48, which makes sense because this is a very concentrated and very strong acid. So our pH is negative 0.48. So let's look at this problem. Sodium hydroxide is a strong base that also completely dissociates, which means that it pops apart into sodium ions, and hydroxide ions when it's dissolved in water. Let's determine the pH of a 3 moles per cubic decimeter, 3 molar sodium hydroxide solution. So can I go ahead and just do the negative log of the concentration of the base here, and we're going to get, oh, the same number as we got on that last slide. Does this make any sense? Can my base, sodium hydroxide, have a concentration of negative 0.48? That's really, really less than 7. That doesn't make any sense. My base should have a pH much, much greater than 7, right? And the reason is this. Hydroxide polyatomic ions are not the same as hydrogen or hydronium ions. In fact, they're kind of the opposite. Remember that when we have acid and base neutralization, these guys bind together and cancel each other out when they make water. So I cannot use hydroxide as my hydrogen ion concentration when I'm finding pH. Instead, we have this magical thing called the pOH. So this idea of pOH is super similar, almost the same as pH. The only difference is what kind of solution we're looking at. So with pH, we're looking at the negative log of the hydrogen ion or hydronium ion concentration. In a pOH, we're looking at the negative log of the hydroxide concentration in a solution. And what's really cool about any solution, the pH and the pOH will always sum up to 14. So we can take any solution. If I add the pH and the pOH, we're going to get 14. And that number is based on the equilibrium concentration of water ionization. So water will dissociate into hydrogen ions and hydroxide ions. We've talked about this before. What's super cool is that these guys will dissociate at equilibrium with concentrations of 1 times 10 to the minus 7. And so if I'm looking at something that's neutral, the hydrogen ion concentration is going to be 10 to the minus 7. The pH, whoa, that's a weird P. The pH is going to be equal to the negative log of 10 to the minus 7. That's going to give it a pH of 7. The pOH of a neutral solution is also going to have a negative log of that hydroxide concentration, 10 to the minus 7. That's also going to be 7. So the pH of a neutral solution is 7, the pOH is 7, because the hydroxide and hydronium ion concentrations are both equal to 10 to the minus 7, because water at equilibrium dissociates at a concentration of 10 to the minus 7 H pluses and 10 to the minus 7 OH minuses. So let's take this idea back to our problem about hydroxide. So we're going to find the pH by first finding the pOH, because I have sodium hydroxide. So I can find the pOH of sodium hydroxide is going to be equal to the negative log of the hydroxide ion. My pOH is going to be equal to the negative log of that 3 moles per cubic decimeter. And again, my calculator gave me a 0.48. Negative 0.48 is the negative log of 3. So this is my pOH. Remember that pH plus pOH is always going to equal 14. So if I plug in negative 0.48 as my pOH, I can solve for pH. pH plus negative 0.48 is going to equal 14. Add negative, well, I guess just add, not negative. Add 0.48 to both sides, and the pH is going to be equal to 14.48. Super crazy strong base, which makes sense because it is sodium hydroxide. And this is a pretty concentrated version of sodium hydroxide. So here we're going to switch things up a little bit, and I'm going to have us find the H pluses, the hydrogen or hydronium ion concentration, and the hydroxide concentration if we're given pH first. So I have the pH, I want to go backwards and find those concentrations, hydronium ion and hydroxide ion. Remember that when we found pH, we were finding the negative log or the negative common log of the hydrogen ion concentration. I was trying to figure out 10 to what power was equal to that hydrogen ion concentration. This, the negative version of this, gave us the pH. So all I'm going to do is take that pH and put it back into its exponent spot. So if the pH is equal to 6.70, and this is the negative log of the hydrogen ion concentration, then if I make this the exponent on a 10, the negative exponent on the 10, then I'm going to have my hydrogen ion concentration. H plus will be equal to 10 to the negative 6.70 power. And I can plug that into my handy-dandy calculator, 10 raised to the negative 6.7 power, and we get H plus, that was a crazy bracket. Let me start that over so that you can actually see what I wrote. Hydrogen ion concentration is equal to 1.995, so many digits. I'm going to do some sig fig stuff and get 2.00 times 10 to the negative 7 power. This is my moles per cubic decimeter concentration of the acid here. Good? All right. So now we need to also find the hydroxide concentration. We're going to do that not with a pH, but with a pOH. So remember that pH plus pOH equals 14. So if my pH is 6.70, add that to the pOH, we get 14, subtract 6.70 from both sides, and pOH is going to be equal to 7.30. So now this is my negative exponent on the 10. Remember that for our common logs, we're trying to figure out 10 to what power is equal to n. This is my power, my pH, my pOHs are the powers. So I'm just going to take those and put them back as the exponents on a 10, but make them negative because it's the negative log. So my hydroxide concentration is going to be 10 to the negative 7.30. With my handy-dandy calculator, 10 raised to the negative 7.30 power, and I get a concentration of 5.01 times 10 to the minus 8 power moles per cubic decimeter, or molarity. So I definitely have a little bit more H plus than I have OH minus in this solution, which makes sense because my pH of 6.7 tells me that it's an acid. I should have more H pluses than I have OH minuses, otherwise I'd have a base. And here are more problems just like the one we just did. Highly recommend pause the video, try to do these on your own, restart the video and check your answers. Good? All right. Here are some answers. So pH of 4.5 means that the hydrogen ion concentration is going to be equal 10 to the negative 4.5. Plug that into my calculator, 10 to the negative 4.5, and we get 3.2 times 10 to the minus 5 molarity, or moles per cubic decimeter. If the pH is 4.5, the pOH is going to be 14 minus 4.5, which is going to give me a 9.5. Take that hydroxide concentration. The hydroxide concentration is going to be equal to 10 to the negative 0.95. Plug that into my calculator, 10 raised to the negative 9.5, and we get 3.2 times 10 to the minus 10 power. What if I have a pH of 10? My hydroxide ion concentrate, hydronium first, hydronium first, is going to be 10 to the minus 10. I can do this one without my calculator. It's going to be, well, 10 to the minus 10, or 0.12345678 10 is my 1 moles per cubic decimeter, or 10 to the minus 10 molarity. So what's the pOH? Remember that pOH and pH add up to 14, so 14 minus my pH of 10 gives me a pOH of 4. My hydroxide concentration is going to be 10 to the minus 4. pOH becomes the negative exponent on the 10 to find the hydroxide concentration. I can do this one without my calculator. The hydroxide concentration is going to be 0.1234 molarity, or moles per cubic decimeter. Notice that this concentration is much, much, much greater than this concentration, which is why the pH is greater than 7. It's why it's a base. All right, let's do one more. pH of negative 1.08. This is crazy super strong concentrated acid. Negative 1.08. So my hydroxide concentration is going to be 10 to the negative 1.08. Negative negative makes it a positive. So my hydroxide concentration, hydrogen, oh my gosh, hydrogen ion concentration is going to be 10 raised to the 1.08, and that is equal to 12 molar or 12 moles per cubic decimeter. This actually is the concentration of the hydrochloric acid that we buy from the chemical supply store. So we do actually have in our lab some 12 molar pH of negative 1.08 hydrochloric acid. It will melt your face off. We use it only in the fume hood. Let's figure out what is the hydroxide concentration of this guy. So if this is my hydrogen ion concentration, what is the hydroxide concentration? Remember that pOH is going to be 14 minus the pH. And if I negative a negative, we're going to get the positive. So the pOH is going to be 15.08. This becomes my negative exponent on the 10. 10 to the negative 15.08 is going to give me 10 raised to the negative 15.08. Calculator says 8.3 times 10 to the minus 16 molar. That's tiny, 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 which makes sense because I have so much H pluses. So those H pluses and OH minuses, they kind of work with and against each other. The more H pluses you have, the fewer OH minuses you have. The more OH minuses you have, the fewer H pluses you'll have. All right, we're going to do 2 more problems and call it a day, my friends. So let's say that I've got 50 cubic centimeters of 3 moles per cubic decimeter hydrochloric acid, and I'm going to first dilute it by adding it to some distilled water. What is the pH of the resulting solution? So before I can use my negative log of the hydrogen ion concentration to find the pH, I need to work on my dilution here. So remember that our dilution formula, M1V1, M2V2. So here is my V1 and my M1. So M1 is 3 moles per cubic decimeter, also known as 3 molar, and 50 cubic centimeters. That's the same thing as a milliliter, remember. I'm going to set that equal to M2. I don't know. V2, be careful. This is not actually my V2. Because I'm adding these together, my V2 is going to be the sum of 2.5 cubic decimeters and the volume that I started with, 50 cubic centimeters. These labels don't match. Let's make them match. I'm going to turn them into all cubic centimeters. 2.5 cubic decimeters. Multiply that by 1,000. Whoops, I have too many zeros. Multiply that not by 10,000, just by 1,000. I got excited about my zeros. Cubic centimeters, add the 50 that we started with, and so my new volume is 2550 cubic centimeters. 2550 cubic centimeters. Good. Now I can go ahead and solve for my new molarity. Molarity is going to be 3 times 5 divided by 2550. 3 times 50. 3 times 50 divided by 2550. And our new concentration is 0.059 molar or moles per cubic decimeter when I do my sig figs. This is not yet my final answer, my friends, because I want to find the pH, not the concentration. But I know that this is an acid. I know that it's a strong acid. It's going to completely dissociate. So if my hydrogen or my hydrochloric acid concentration is 0.059 molar, then my hydrogen ion concentration, because this is a strong acid that completely dissociates into H pluses and Cl minuses, is also going to be 0.059 moles per cubic decimeter. So to find the pH, we're going to take the negative log of that number, 0.059. Handy dandy calculator tells me that the negative log of 0.059 is equal to 1.23 with my sig figs. Here's my final answer. The pH of this diluted acid is going to be equal to 1.23. Good. All right, let's do one more. So this one is super similar except for 2 big things. Number 1, I have a base, not an acid, and anytime you see that OH, you need to be thinking ding, 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 ding. I need to work with POH because it's a base, not an acid. The other thing that's a little bit tricky with this problem is I'm starting with the pH, not the concentration. So I'm going to have to take this pH, find the POH, turn that POH into a concentration, because then I need to do my dilution formula. And then finally we can find the POH of the new solution and use that to find the pH. Are you ready? If the pH is equal to 11, then the POH is going to be 14 minus 11 is equal to 3, which means that the hydroxide concentration is going to be 10 to the minus 3, or 0.001 moles per cubic decimeter. This is my M1. This is my V1. Again, I'm adding things together, so my V2 is going to be 550 cubic centimeters plus the 50 over here that we started with, and so my new volume is going to be 600 cubic centimeters. So when I do M1, V1, M2, V2, M1 again is going to be this guy that I found from the pH that led me to the POH that led me back to the concentration. Molarity is 0.001 molar or moles per cubic decimeter. My volume that I started with was these 50 cubic centimeters. Set that equal to M2, I don't know yet. V2 is the sum of those two things that I added, that base and then the water, is 600 cubic centimeters. Multiply and divide, and our new molarity is going to be 0.001 times 50 divided by 600, and we get an 8.3 times 10 to the minus 5 molar or moles per cubic decimeter. This is my hydroxide ion concentration. I can find the POH if I take the negative log of that hydroxide concentration. The negative log of 8.3 times 10 to the minus 5. My handy dandy calculator says 4.08. 4.08 is my POH. That pH is going to equal 14 minus my POH. 14 minus 4.08 is going to give me a pH of 9.92. And this makes sense because I had a super strong base of pH 11 and I diluted it with water, so it is not as concentrated a base, which means that my pH should get closer to 7, and it did. We went from 11 down to 9.92, which is closer to 7. We did it! And we also achieved all of our objectives. We talked about the pH scale, we reviewed logarithms, we used the logarithms to find pHs and POHs, and then we went backwards and put our logarithms back as exponents to find concentrations. Good work today, my friends.